We've come across one family of hydrocarbons, of organic molecules, called the alkanes, and here they are. We've got methane, ethane, propane, and butane. They're composed only of hydrogen and carbon, and they've got the general formula CnH2n plus 2. Okay, so if n is equal to 4, then the number of hydrogens must be twice that plus 2, so that's 10. Now we're going to come across another family of organic molecule called the alkenes. So the difference in the name, they just got an E there, alkenes. Now what they contain is they contain a double bond between two carbon atoms. So if I draw that there, obviously you can't have a molecule with just one carbon in. You've got to have a double bond between two carbons. So this each carbon always needs to form 4 bonds. So this carbon would need 2 hydrogens. The double bond counts as 2. And this carbon would also need 2 hydrogens. That is actually called ethene, not ethane, but ethene. And the formula of that one would be C2H4. If you look at the next one along, so with 3 carbons in it, so 3 carbons, put a double bond between 2 of them. So the carbon on the far right is going to need 2 hydrogens. This middle one is going to need just 1, so it's forming 4 bonds, and the end one's going to need 3. The formula of that would be C3H6, and that is called propene. Just do one more, the one with 4 carbons in it, so we want 4 carbons in a row. Put a double bond between 2 of them. So the carbon on the far right, to make 4 bonds, is going to need 2 hydrogens. The next one along is only going to need 1. The next one will need 2. And the end one will need 3. That is called butene, not butane. And that has got a formula of C4H8. So if you want to look for a general formula for alkenes, then you can probably see, if you look at them, the ratio of carbons to hydrogens is always CnH2n. Okay, so there's another family of hydrocarbons, and they may think just having a double bond doesn't make much difference to their properties, but it does, as we'll see in later videos. It gives them, it makes them more reactive than alkanes. And we tend to call those, they are called unsaturated. Unsaturated means that they contain a carbon-carbon double bond. If you like, they're not saturated with hydrogen. There's not as much hydrogen in them as there could be, because look, it's only C4H8, whereas the corresponding alkane is C4H10. So that's unsaturated alkenes, and the alkanes are called saturated hydrocarbons. So there's 2 fairly important words to know. Right, now let's talk about cracking. So, right, the problem with crude oil is, you see this pie chart here, is most crude oil, around about 50% of it, is the very heavy fractions, the bitumen. When we say heavy, we mean they've got long carbon chains. That means they've got high melting points and boiling points, high boiling points. And the higher the boiling point means that they're not very flammable. And as they're not very flammable, that tends to mean they're not very good to use as fuels. Whereas if you look at the shorter ones, so petrol, diesel, and kerosene, these shorter carbon chains are more flammable and more useful as fuels. So there's a problem. So every time like a barrel of crude oil is extracted from the ground, only about half of it can be used as fuels. The demand for bitumen isn't that great. Yes, they use it on roads and stuff, but people don't want that so much. So what do you do with the other half of the barrel of oil? You can't throw it away. One, that'd be very wasteful. Two, it'd be very environmentally bad. Well, the solution is you get these long molecules, and which aren't very useful, lots of carbons in the chain, and you break them down into larger number of shorter molecules, and those shorter hydrocarbons are useful as fuels. So we're going to have a look at cracking now then. So how is cracking carried out? Well, you just get the heavy fractions, the bitumen, and you heat it in the absence of oxygen, because if you heated it with oxygen it would burn. Absence of air, high temperature, and the molecules will collide with each other. Sometimes they'll collide with sufficient force that you will break some of the carbon-carbon bonds. Okay, so let's have a look at that. So what I've got here is I've drawn a hydrocarbon. I think you find that it's 15 long. So you remember the formula, that should be C15. So the number of H's is going to be 2 times 15 plus 2, 32. And we're going to break that molecule here. So it's being cracked by having another molecule colliding into it. And that's broken the carbon-carbon bond. And you get these two fragments below, here and here. Now you can see there's a problem with this carbon atom on the end here is only forming 3 bonds. And of course it's got to form 4. So what happens is a double bond forms between those 2 carbons. But then there's a problem because it means that this carbon is forming 5 bonds. And of course, so one of the hydrogens has got to drop off there. So that drops off. And that hydrogen, we'll draw it there. Well, if you look at this carbon now, this isn't forming enough bonds. Well, that's what happens to the hydrogen. It sticks on there, forms a bond there. So you end up with 2 products. And you can probably see that of those 2 products, the one on the left is an alkene because it's got a double bond, whereas the one on the right is an alkane. So let's write an equation for that, a balanced equation. So in that case, we've got C15H32. Goes to make this alkene, well, that is 6 carbons long, and if you count up the hydrogens, it's going to be 12, so that's C6H12. You can tell by the formula there it's an alkene, because if you look, it's CnH2, and there's not plus 2. And plus you're going to get this alkane, well, that is 9 carbons long, so that's C9. And hydrogens, will double it, 18 plus 2, because it's an alkane, 20. Now, if you add all that up together, you can see that that equation is balanced. And we should also always notice that when you carry out cracking, you always start off with an alkane, and you always make another alkane, which you've got there, plus an alkene. And we'll have a look at that, another example of that in a minute. Okay, so that's what happens in cracking. Just incidentally, you probably wouldn't bother wanting to crack this molecule that was C15 long, because that's short enough to be a useful fuel, but obviously I'm not going to draw one that's 50 long because it would take too long. Okay, but the principle is the same. Right, let's have a look at another example of cracking. I've got another one here. So again, I've got C15. This is C15H32. The alkane, and we're going to break it in these where the greens are. Okay, you're going to break those bonds, so we end up with the following molecules below. Now you can see that there's been some arrangement. We form some double bonds. We form a double bond there, new double bond there, one there, and one there. And there's been some arrangement of the hydrogen atoms, so that red one there has fallen off and it's ended up there instead. That yellow one, that's had to come off because the double bond is formed, and that's ended up there. Okay, and I should have done that one in green, this one here, this green one, that's ended up there. Right, so let's write a balanced equation for that one. So that's fragmented in multiple places like the other one, so we're going to get C15H32 32. And you're going to get this, the first one on the left, which is C4H8. And then you're going to get this one, which is also C4H8. So I should get rid of that really and put a 2 in front. Let's do that. And then you're going to get this one, which is C5H10. And finally, we're going to get an alkane at the end, that is C3H8. So we just look at what we've got there. This is an alkene, you can tell by the ratio of carbons to hydrogens. This is an alkene, and this is an alkane. So whenever you crack, you always get one of the fragments is an alkane, and all the other bits are alkenes. And right, what causes it to crack in certain places? Well, it's just purely random, okay? Obviously, you can probably guess if the temperature is higher, then you're going to get it breaking in more positions, so you're going to end up with smaller fractions. Let's look at one more example before we finish. Okay, so this time, again, we've got C15H32, and this one's going to break up into lots of small fragments. No, so that's going to break up into two fragments. And so what we got there, we have got C5H10, and this one is C10H22. That one is an alkane. That was an alkene. So once again, the same pattern. You always get one of the fragments is an alkane and the others are alkenes. And you can see that this red hydrogen here has had to fall off and stick on there, and we formed a new double bond there. Last one. Right, this is going to break up in multiple places, okay? So what we have got again is you've got C15H32, and it's going to break where all those green breaks are. Right, so when it does that, we are going to end up with those fragments below. So what I'm going to do is put a double bond there. Now that means that doesn't need any hydrogen sticking on. Now don't forget that red hydrogen has dropped off. That's going to have a double bond there, double bond there, double bond there, double bond there, double bond there. All of those carbons are forming the right number of bonds. Now this last one here, well, the red hydrogen from over here, that is going to stick on the end there. So if we write an equation for that, we have C15H32 forms 1, 2, 3, 4, 5, 6 of these ethene molecules. So 6 C2H4. They're all alkenes. And then finally one alkane, C3H8. And we'll see later that ethene is actually a very important product from cracking. Ethene can be used to make plastics. Probably heard of polyethylene, which we'll come to in a later video. But for now, we'll leave that there. That's cracking, breaking less useful big hydrocarbons down into more useful smaller ones. And when you do that, you introduce double bonds. When the molecule's got a double bond in it, no longer an alkane, it is an alkene.